What's going on, everybody? This is Mr. Diamond, and we gotta get our laser pointer here. We're gonna be going through the next part of Chapter 4 in physics related to speed and velocity of circular motion. We're gonna talk a little bit more about those things, and we're gonna talk about acceleration in this section. So for our next point, we're gonna talk about how we apply them in the case of circles a little more. We have our equation for calculating it, but we had a little bit of an issue that we had talked about. The speed of objects moving in a circle is constant. It's going to have the same speed as it's going around there. But its velocity is actually not going to be constant. We mentioned there were some issues with velocity in the first place, and that, like, if you look actually across the circle, like on the opposite point, you would think you could just draw a straight line to calculate the velocity, but you really couldn't. But there's another issue related to velocity. Remember, velocity is a vector. It's not just a displacement instead of distance traveled, but it's actually also a vector. Speed isn't a vector, so the direction that it's pointing actually doesn't really matter. But velocity is a vector, which means it actually does care about the direction that it's going. So as it's going, we actually position our velocity vectors, the speed, if we have a point that's moving right here, if this is going clockwise, if it's going to the right, its velocity vector would point to the right. We actually would say that it is tangent to the circle at any given point. Hopefully you're still feeling pretty okay about what that means, but it means that it intersects at exactly the point that it's there, but then goes completely off to the side. If it's clockwise this direction, if it's counterclockwise, it would be to the left here. So at every given point, it's actually slightly changing the velocity, which means even if it's rotating at a constant speed, remember our definition for acceleration is change in velocity over time, which means while the speed would be constant, the velocity is not, and therefore there is always an acceleration if an object is rotating, even if the speed is constant, even if it's rotating at 20 RPMs, 30 RPMs, 20 meters per second as a linear velocity, etc. If it is going at that speed, at that unit of speed, at every given point, the velocity is changing very slightly. Even if you just go very slightly along the curve, if one's pointing here and one's pointing here, that's still a slight change in the velocity. So always an acceleration if you're in a circle. This actually makes sense if you think about it backwards. When you're on like a carousel or a tilt-a-whirl or anything that's rotating, you feel that rotation. You can feel in your body, you have a sense that it is rotating, even if it's rotating at a constant speed. And that force you're feeling with is coming from a force, which cannot happen, if you remember from a couple chapters ago. Forces come from masses that are accelerating. They're going through some kind of acceleration. You can't have a force without an acceleration. So if you're feeling that force when you're going through some sort of turn or when you're going through a rotation, you have to have an acceleration somewhere. To calculate this acceleration, we'll use a version of the same equation, but I also want to bring up another question, which is which direction does this acceleration point? Because the force that we're feeling and the acceleration that we're feeling have to be going the same direction. And so most people get into this sense where they have this very, very, very common misconception that it points away from the circle, that the object will actually point out of the circle. But that is not the case. And in class, we'll do this by looking at the velocity vectors. We'll break them down. And we'll talk about a couple of hypothetical situations in a second here. But the vector actually does not point outwards. It actually points inwards. It's the opposite direction that it's going. So most people call it a centripetal force. Centripetal force is what we would call the force, but it points inwards. Centrifugal force or centrifugal force, as a mispronunciation of it, is the idea that it points outwards, and that's not actually the case. That has to really do with inertia. And again, we'll look at the example here in a second, and you'll kind of see a little bit better. But notice this whole tangential velocity thing. This is a big reason that we'll use for our proof. And you can actually prove this by watching any video footage or camera footage of people that are like spinning an object on a string, which we'll try to do in class, but it's a little hard to see. When you let go, the object doesn't actually go straight out. Like if I'm swinging and I let go of it whenever it's going around the circle and it's right here, it's not going to then go straight off into the distance. It's going to continue the path that it was going. It's going to continue on a tangential velocity. And that's also part of how we know that the velocity must be pointing tangent to the position that it's at on the circle. So if we come back here, if an object is going to continue down that path, it kind of leads to the misconception when you are inside of the circle, when you're in the frame of being rotated, it feels like you're being pushed out, but that's not actually the case. So the two common examples to prove both of these points. So first, to kind of prove our idea of the velocity going that direction, a really common example is, you could think of like a merry-go-round, but we can even go with like a basketball that's spinning. If you've ever tried to do this, you know that when you spin it, you need to get it going, and then if you want to keep it going, you have to hit it just like in this GIF here. You have to kind of hit it to the side. If I want it to keep rotating in a counterclockwise, I have to be adding velocity this direction. So I'm going to be applying a force in that direction to hit it. I'm adding a force this way because I'm trying to make the velocity go this way, and it's going to cause the point to spin around on the ball. Now, for the acceleration here, we can actually look at a car going around a curve, and this is something we're going to get into a little bit later on whenever we start applying this. But for an object to go around a curve, that curve is just a part of a circle. There needs to be some type of force keeping it inwards. That inward force is what allows you to go around the curve, and it actually comes from the friction on the tires of a vehicle. That frictional force is what allows you to take this rotation. And if you don't have it, if that frictional force pointing inward is not enough as you go around that curve, you will see that the people will slide off. They'll go off in these straight lines. They'll go off in this direction here. And that's exactly what's happening when you are like in a car that goes around a curve. If you feel yourself getting pushed the opposite direction of the curve, that's because your body is trying to continue the path that it was going on. It has inertia, it has momentum. And so while it's trying to go that path, the car is moving this way, but your body wants to keep going this direction. And if you were to look at that, you would see that it looks like you're being pushed out, when in reality, you're just trying to continue in a straight path. And the car is going to knock you back that direction. The car is actually going there. You just don't have enough frictional force on your seat to keep you in place. Your centripetal acceleration, your force going inward, is not enough, and it's causing you to push out that direction. So it looks like you're going out when you're in the act of going through the circle. It feels like you're being pushed out, but really it's the fact that you don't have enough acceleration pointing inwards, and your body is trying to carry on that inertia. Now, depending on, or deriving the actual equation for this is very weird. I mentioned in class a little bit, it involves looking at like the similar triangles, and there's some weird stuff that I'm not very comfortable with, and I would probably misspeak if I tried to explain it. So instead, we're going to look at our equation just here. You just kind of gonna have to have it. You don't really need to know anything else related to it. Acceleration centripetal, so the centripetal acceleration that points into the middle, is equal to the velocity squared divided by the radius. That is our centripetal acceleration equation. And then while we're here, we may also just go ahead and mention another way we can calculate it is if we have our angular velocity. So this was the whole idea we talked about. Linear velocity is different for different points on a circle, but angular velocity, the change in angle, is the same. If you know that number, you can actually also calculate acceleration, but we're mostly not going to worry about that. I just wanted to point this out while you're here. That angular velocity is less convenient, but it is another way you can find the centripetal acceleration. We'll actually kind of look at this in a second, or in class. There's a video. We may not watch the whole thing. I'll post it in Google Classroom. I should attach it somewhere. It's probably attached to the weekly agenda. If not, let me know. But there's a couple of videos related to this that kind of explain how the force works a little better. It's a weird concept, so I wouldn't blame you if you're still a little confused as to how exactly it works. But we've got two examples here. One is a car moving around a turn with a circle with a radius of 25 meters, and the other one is a student sitting on a merry-go-round feeling a certain constant force. And again, that force will allow us to use acceleration. So not only will we be able to use our new equation that we talked about a second ago, the acceleration equals velocity squared over radius, you can actually then also plug information into or get out of F equals ma to solve for acceleration, and then also figure out like linear speed, for example. But that's all I've got for this video. They should be attached to this, a video where I go through the two example problems there. If you have any questions, shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.